Okay, well, great. Everybody's welcome back. Today we're going to start into something more serious. I think, as I mentioned, the lectures up to this point have been kind of an overview of computational intelligence and its limitations, especially artificial intelligence, from a philosophical, scientific, and, if you will, an opinionated point of view. And I hope that you enjoyed it. Today we're going to get down into a little bit more mathematics, a little bit more deeper into the theory of computational intelligence. Computational intelligence is more than large language models. It's more than deep fakes. It's very broad. The IEEE Computational Intelligence Society has a number of publications. Yeah, computational intelligence in the theory of games. There's an evolutionary computation, a transaction which applies the idea of random search to engineering problems. Very fascinating area. Another one is the transactions on fuzzy logic. There's the transactions on neural networks. I used to be the editor in chief of that a few decades ago, and it's still going strong. It's one of the most highly cited of all the artificial intelligence journals that are out there, serious journals that are out there. So we're going to talk about fuzzy logic specifically. We'll also talk about later swarm intelligence, which is one of my favorite things. We've all have heard of swarms of drones, for example. Some people consider this some of the most important and dangerous of all weaponizations of technology. In other words, you can be attacked by a whole bunch of different drones, and it's just difficult to take them all out. So we'll talk about swarm intelligence a little bit. We'll talk about evolutionary computing, and we will talk about neural networks, specifically those things which are trained using error backpropagation. Uh, Discovered again. I want to give this guy credit because he doesn't get very much credit. Discovered by Paul Werbos in 1975 in his Harvard PhD examination. So with that, let's go ahead and start about fuzzy logic. The interesting thing about humans is that we communicate in fuzzy terms. We talk about a person is tall. We talk about a person is short. A person is fat. A person is ugly. Some of these things are ordinal. Like, for example, when a man is tall, you can say, well, tall is, 6.2 feet. And what you're doing is you're giving an ordinal number to that. And so we still, nevertheless, we don't talk about men, 6.2 feet taller, being 6.2 feet or taller as being tall people. Um, but we do talk about tall people without really differentiating what the difference is. And this is a problem. I've noticed that most law is written this way. Um, for example, when you go to trial and you're on a jury and somebody is up for murder, you have to be assured before you vote them guilty that they are guilty beyond a reasonable doubt. Reasonable doubt, that's a fuzzy sort of term, and is one which is not ordinal. There are some things, unlike tall, that we still can talk about in terms of their rankings. Um, we can talk, for example, about how beautiful a scene is. We can talk about how wonderful something smells. It does turn out, at least this used to be the case, that in the U.S. Patent Office, you could not patent aromas or tastes. You could probably if you were able to reduce it to some sort of technology, to some sort of chemical analysis, you could probably patent that. But the idea of a smell or something is nothing that you can really patent. Yet we can talk about how things smell good and how things smell bad. And these are fuzzy, non-ordinal sort of judgments. Um, so there's a number of them. One of them is when you go to the hospital. I broke my wrist a number of years ago and went to the emergency room, and see, I got a little thing. You probably can't see it, but they put a little iron thing in my disc. I ran outside and I was running back inside and I tripped over a pothole. Actually, I don't tell people that. I tell people I broke my wrist by doing skateboarding down a rail at Alderwood Mall. But that isn't true. If you break your wrist, come up with a good story. Don't tell them the truth. The truth is, I tripped over a pothole and I began running, and I got out over my skis, as they say. My head got further and further in front of my body, and I fell down and I smashed into the ground, and my glasses fell off, and they were kind of looking at me, and I was lying there face down to the parking lot, and I was trying to assess how I was doing when I heard this far off lady's voice said, "Are you okay?" And I said, "Yeah, I'm okay." And so I got up, collected myself, and decided to just go home. And but my wrist started to communicate to me in little throbs, kind of a Morse code. Okay, your throbs are kind of like a Morse code, and it was communicating to me that something was wrong. So I went to the hospital, and one of the things that they ask you, and I'm sure that you've been asked before, is on a scale of 1 to 10, how much pain do you have? Now, the amount of pain that you have cannot be quantized. I was told about 30 years ago, if you could actually quantize pain, I was told this by a medical doctor, that you would be doing pretty good. That the best we can do now is just give a fuzzy description of pain on a scale of 1 to 10. And that's what they asked me at the hospital. And I said, oh, it's about a 3. And then they wheeled out this was very interesting. They wheeled out this thing. I don't know if you've ever seen this Chinese finger trap where they have this little loop and you put your fingers in both ends, and the harder you pull, the more it resists you separating your fingers. Well, these are more one-ended Chinese torture things, and they put them there, and you put your hand in it, and you put the hand down. They put like a 6 pound weight on my arm, and that really straightened out my wrist. And boy, that felt a lot better. So my pain went down to about a 1. And then the guy came in after the X-ray and said, "You have to get your wrist adjusted." I don't know if you've ever heard about about the idea of resetting a joint. I said, "Yeah, okay, reset my bone." So he grabbed it and massaged it, and I thought, well, that wasn't bad. Then all of a sudden there was this incredible jerk, and it was an incredible pain. And I told him, "Oh, that pain thing just went up to 9." Okay, it was a fuzzy linguistic variable. It's not ordinal. You can't measure pain in terms of numbers, but you can assess it on a scale of 1 to 9, or 1 to 10, if you will. And that's basically what fuzzy logic is. It can be applied to non-ordinal things such as pain, but it can also be applied to ordinal sort of measures, such as how fast somebody is going. Boy, that guy was really running fast. That's fuzzy. That's a fuzzy linguistic variable, even though you could measure it in terms of how fast they were running in miles per hour. You could actually give a number associated with it. So we use fuzzy logic for both ordinal and non-ordinal things we can measure and things that we can't measure. So that's the basic idea of fuzzy logic. So with that, let me share my screen and show you some things which you will be interested in, I believe. So you can see here the sheet for the class. I've given you a number of different links here, and these are resources for you. One is a fuzzy logic tutorial, and let me open it up. Whoop, I always forget how to open stuff up here. Okay. This is a tutorial about fuzzy logic that I wrote a number of years ago for the CIA lab. Now you might be thinking, well, the CIA lab, well, that was a lab here at Baylor, and that stood for the Computational Intelligence Lab. So we called our lab the CIA lab, not to be confused with the government equivalent of it. But this is a very nice. I think it's nice because I wrote it. It's a very nice tutorial about the material that I'm going to cover. And there's lots and lots of material on fuzzy logic. And so this is the introduction to the idea of fuzzy logic. And you can see, you can take a look at that. Okay, so that's one of the things that I gave you as a resource. The other thing I did was I provided a link to Latfizada's 1965 paper. Now, I tell you, the the forcing function for publications of university professors is so great. You don't get great papers anymore. You get a bunch of papers that are kind of 3DB. That I've heard it called salami science. The salami science is in the sense that you take your research and you slice it into the thinnest slices possible in order to um, get a number of lists longer on your resume. Because there's the old saying that the dean can't read, but the dean can count. So the dean can't read your papers and doesn't understand your papers. I don't think any dean can, because at least in electrical and computer engineering, things have become so broad that nobody understands everything anymore. So there aren't the great papers that there were in the past. And if you look, for example, at Claude Shannon's 1948 paper, where he invented information theory, and I teach an entire class, based on Claude Shannon's original work. The search engine Claude is named after him. If you remember, he was involved in the 19, I believe it was, um, the Dartmouth conference where the term artificial intelligence was formed, and it's just a beautifully written paper. This is also true of Zada's original 1965 paper, because his original 1965 paper is just brilliant. He outlined the idea of fuzzy sets and just did so wonderfully. He only passed away, I think, I don't know, a decade or so ago. He was with the University of California in Berkeley and was just a wonderfully, wonderfully pleasant man. I did get to know him after he became famous. I have this web page called My Brushes with Greatness, and I have pictures of me with famous people. And so I have a picture of me with Latfi Zada. And he actually wrote the foreword to a book that I put together on a collection of classic papers in fuzzy logic. And when I asked him, he says, I say yes to everything. So anytime he was asked to do something, he always said yes. Now, the interesting thing about Latvizada is that I don't know if I should share this. Yeah, I probably should. You got to be careful in the pursuit of fame and the development of your career. If you remember Charlie Kirk, the guy that was just killed, he said the most important thing you can do is raise your kids and be with your kids, and don't pursue your time together. Don't pursue your greatness, if you will. That is, pursue your personal life, your spiritual life, and that's the most important. Once you have that established, you can work on your career. And I don't know if Zada did this, but one of his sons, who was named Norm Zada, and if you want to look at him, he's on Wikipedia. Norm Zada grew up. He did get a PhD, and he was really big into gambling. Wrote one of the best books on gambling that's still available, I believe. But then he said, that's not where the money is. So he became one of the leading pornographers in the United States. So Latvia Zada's son was one of the biggest pornographers in the United States. So yeah, so Latvizada had a great career, but his son went astray. Maybe not to the fault of Latvizada or not, but you just have to wonder, if you will. And then I have also a link to chapters by Clear and Folger here. Clear and Folger wrote this wonderful book on fuzzy logic that I still appeal to today because it was written so well. And they actually go through the math. It turns out that there's lots of things that happen in mathematics that people mess around with, and they don't actually go back and carefully define it from the axiomatic viewpoint. Axiomatic meaning like Euclid's Elements, where he went back and formed planar geometry from, I believe, 5 axioms. Uh, Kolmogorov did this with probability. He came along, and I believe he also had 5 axioms. I'm not really sure. But he had these 5 axioms, these statements that are so true that nobody can argue with them. And from that, he was able to develop all of probability theory. Well, that's what Clear and Folger do for fuzzy logic, and they do a wonderful job of it. And we'll be referring to that occasionally, and I'll be giving you some homework from that also. So those are resources that are available to you that you can take a look-see at, as I refer to them, and as we wade through this material. Okay. And it turns out that we could spend a lot of time talking about different fuzzy ideas. And we could do that because my goodness, there's still an entire journal dedicated to this, and new applications of fuzzy logic are coming out all of the time. As engineers, we're primarily interested in reduction to practice. So I'm going to tell you about fuzzy inference. And fuzzy inference was not coined by Latvizada. It was coined by a guy named Mamdani. And I guess that's a common Indian name because if you follow the news, there's a guy named Mamdani running for the mayor of New York City right now. And it's not the same Mamdani, it's a different Mamdani. And we will talk about his fuzzy inference and his extension of Zada's idea of fuzzy logic to things such as control theory. Now, when fuzzy logic first came out, it was very controversial. I told you about my work with Boeing on anti-skid devices and automatic braking systems based on fuzzy logic. At the time that I worked with Boeing, that I consulted for Boeing, they had a kind of a mechanistic way of doing things. It was classical control theory, probably with Laplace transforms and things of that sort, for those of you that have taken classes in control theory. But the control system was very mechanistic. It was such that it was there and now something didn't work, so they slapped a new piece of technology on it, and something else didn't work, and so they slapped a new piece of technology on it. So it became kind of, if you will, mechanistic. And we came up with a technique using fuzzy logic that was able to land the airplane without problems. And I mentioned to you before, and I'll mention it again because it's so funny. I learned what the derivative of acceleration was. It's called jerk. And then because when your acceleration changes, you jerk. And the derivative of jerk is snap, then crackle, then pop. So uh, that's what happens as you do the higher and higher derivatives. Okay, but they didn't like the idea. They ran it up the flagpole and they went to the brass at Boeing and they rejected it. They said, no, we can't accept this because nobody's going to want to fly in an airplane which is controlled by fuzzy logic. And there's a lot of people that were critical of the idea of fuzzy logic because fuzzy kind of meant uncertain. And there is a degree of uncertainty to it, but as you'll see, it's very, 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 uh, it's a very, very good way to solve a number of interesting problems definitively. And you can always take this fuzziness and tune out any inaccuracies that you have or it's like any design. Once you design something, it doesn't work exactly the way you want to. So you go back and you begin to vet it and you see what happened in the past and well, it's not doing what you want to do now. So you kind of tune the parameters and pretty soon you get something which is better and better and better. So now one of the things about fuzzy inference is there's always negative people in new technology, including fuzzy inference. And here is one of them, one guy that didn't even like this idea of fuzzy logic. And he didn't like neural networks. It turns out Marvin Minsky, who was at the Dartmouth conference, died, and he said neural networks, no, they're a stupid way to do it. He liked the idea of expert systems because that's where his heart was at. And so you always have this conflict. One of the interesting conflicts was between Fisherians and Bayesians. And the Fisherians hate the Bayesians, and the Bayesians hate the Fisherians. Uh, Bayes' theorem, if you've had probability, actually talks about the probability of events which have already happened. And so the Fisher people didn't like this. And so they said, no, you got to go with the future, with the Fisher. But the Bayesian says what we do is work. What we do, it works. In fact, we apply Bayesian logic to, for example, the filtering out of your junk mail. Right now, your email comes in and it's filtered out and it uses Bayesian logic, Bayesian inference. So yeah, that fight, I don't know if it continues today, but this was a fight that they had a long, long time ago. And so we had this between, as I mentioned, the wars. We had this with artificial intelligence, rule-based expert systems versus connectionists, which is the neural network way of doing things. Here's one guy that didn't like fuzzy logic. Let's see, there he is. It's a guy named Bob Bitmead. And he said the image which is portrayed of the ability to perform magically well by the incorporation of new age technologies such as fuzzy logic. He was primarily considering fuzzy logic, but he also included neural networks. He said this is new age sort of stuff. Approximate reasoning and self organization in the face of dismal failure of traditional methods. Now, Bitmead was a classical control theorist. There was actually an IEEE transactions called, I think, the Transactions on Automatic Control, that you had to have like 6 PhDs to understand some of the contents of their papers. They were so esoteric that they would never be applied. They were just out of left field. And Bitmead came from this background. We start to see it, for example, when you use Laplace transforms, keeping the poles in the proper plane, et cetera, et cetera. He said this, continuing with the quote, he said, "This is pure unsupported claptrap, which is pretentious and adulterous in the extreme and has no place in the scientific literature." Very interesting. Um, so he didn't like fuzzy logic. He didn't like neural networks. This is when it came out. And guess when it came out? It came out in June 1993. So this was a number of years ago. And if anybody argues against the technology, the way that the technology wins, if it's largely reduced to practice. Fuzzy logic has been reduced to practice. Neural networks have been reduced to practice. So if something has been reduced to practice and is making the big bucks, you cannot argue that it is no good, because if before something is reduced to practice, it has to be an order of magnitude better than what preceded it. And that's indeed what we're seeing with neural networks and fuzzy logic and some of these other things. Now, Mamdani, who this quote was aimed at, uh, responded to Bitmead. And I liked his response. And this is something one has to be ready to do when people smash against your ideology. He says, "Fuzzy theories, delayed exploitation outside of Japan teaches several lessons. One is the traditional intellectualism in engineering research in general and the cult, I love this term, cult of analyticity. In other words, just going on with more and more math so you can publish more and more papers. And Mamdani called this the cult of analyticity within control system engineering research in particular. Now, Mamdani, as I mentioned, was the father of fuzzy control. And and this was one of the most widely applied areas of fuzzy logic, is the Mamdani sort of control. And we'll go over what Mamdani control is. It's actually very intuitive, and it's based on the concept of being fuzzy. And then George Bernard Shaw says all progress means war with society. You have an inertia. Here we had an academic inertia of people that wanted to publish papers which were high in mathematical content but little use in practice. And that gets more into the idea of science and philosophy than it does our area of engineering. So you can see there's always been pushback. We're seeing pushback on technology today. I mentioned to a friend of mine, I said, I still listen to podcasts when I commute, but now I've subscribed to the advanced version of Grok, and I have a conversation with Grok as I drive back and forth, and it's really fun. I had a great time talking to Grok. I learned about presidencies. I learned about uh, the development of thermonuclear stuff. Anything that you want to have a conversation with, you can have a conversation with Grok as you're driving along, and it really requires a two-way conversation. If you just listen to podcasts or audiobooks, it's kind of a one-way communication, but with Grok, you can have a two-way communication and dig in deeper if you have any questions. It's really a fun thing to do. But my friend says, "Bob, don't do this. Don't do this. This is wrong." And I wrote back and forth to him and I said, "I don't understand what's wrong. One of the things that I don't do is I don't want to know political sides with Grok. I don't want to get into stories about comparative literature or comparative religion with Grok. So there's areas which have a wide berth of interpretation that I don't want to talk to Grok about because I have my ideas on that. And if they want to give me the broad picture, that's fine. But typically they narrow in on one sort of specific dialogue. It used to be that ChatGPT, for example, was very politically left. It was very woke. They fixed that. It isn't like that anymore. So certainly on political things such as wokeness and stuff, I would never trust a conversation with ChatGPT, at least a few years ago. But they have developed so well, so quickly that now, yeah, I wouldn't mind doing that. And in fact, I do it. It was Ronald Reagan when he was talking about thermonuclear arms treaties that he said, trust but verify. I think with things like Grok and ChatGPT, it's the other way around. You need to verify and then trust. So when you go to these large language models, they say, don't trust what we're doing. Don't trust it. You got to check it out by yourself. And they're very wise to do that. So, yep, I think that in things such as science and facts and history, that yeah, it's pretty good. It's at least as good as Wikipedia. Wikipedia always had problems with accuracy, and I think the Grok does also. So let's talk about so-called crisp versus fuzzy logic. Everybody here is familiar with the idea of crisp logic. You're familiar with set theory. In set theory, something is in the set or not in the set. You can talk about the set of men that are over 6 foot tall. And so if you're 6'2", 6'3", whatever, you're in the set. If you're 5'11", 4'10", you're not in the set. So conventional sets, you're either in the set or not in the set. Fuzzy logic says, well, we can actually talk about sets where you have degrees of membership, and some things are more into the set than other things. We can talk here, for example, about the set of cities that are far from Los Angeles. And we can rate it from a scale of 1 to 10. And usually this is what fuzzy logic is rating things from a scale of 1 to 10, except we don't do from 1 to 10. We do from 0 to 1, if you will, almost like a probability. But we do from 0 to 1. So on a scale of 0 to 1, how much is this thing in the set that we're talking about? So we can talk about the set of cities far from Los Angeles. Notice that the fuzzy linguistic variable here is far. Far is not defined. It's like tall, big, small, whatever. But we can kind of assign it. And by the way, your assignment of the numbers of the membership of these is going to be different than my assignment. This is what I assigned. If we talk about Los Angeles, that's clearly a 0.0. Los Angeles is not far from Los Angeles. If we talk about Chicago, yeah, Chicago is further away, so I'd call it a 0.5. New York is 0.8, and London is 0.9. Now, again, you might come up with totally different answers, totally different measures, and that's okay. But what's interesting about it, I think everybody is going to come up with kind of a monotonicity here. In other words, the Chicago is going to be a smaller number than New York, which is in turn going to be a smaller number than London. So I put my hand up, and so Zoom put my hand up. Okay, I'll take it down. So therefore, the monotonicity would at least be conserved, even though the specifics of your numbers would be different. And that's okay. Fuzzy logic has a great deal of ability to adapt to different numbers and the different ideas that people have about these so-called fuzzy linguistic variables. Um, a lot of sports are measured this way. You talk about, for example, people that dive or ice skating events. Have you ever noticed that there's people on the side with little signs that they rate them on a scale of 1 to 10? Well, that turns out the reason is because it's non-ordinal. If somebody does a dive, you cannot ascribe a specific numerical outcome to that. You can do it to certain things, how much water they splashed and things of that sort. But the overall dive, yeah, it's just hard to quantize. So these experts in divings come out and they talk about how good was the dive. And somebody might say 10 or 9, 9.5, and everybody has a different opinion. But again, that's okay. Fuzzy logic is very resilient to the different interpretations. We can say that if somebody had a good dive, their average on their average score would be higher than somebody that did a belly flop and had a terrible dive. So there is this monotonicity which is applied to here, which we think probably usually applies. Fuzzy linguistic variables are just all over our English language. Other examples include close. How close are we to something? Oh, we're getting close. We're getting close. You notice if you've ever done an Easter egg, you tell the little kids, you're getting close, you're getting close, you're getting warmer, you're getting warmer. All of these are fuzzy linguistic variables. And even though they're not quantized, they communicate very, very well to the little kid finding the Easter egg, how they're doing. You're getting close, you're getting closer, you're getting closer. Um, the idea of heavy, heavy is a fuzzy linguistic variable. Light, if whether an object is heavy or light, something big or small. Smart is something which tries to be quantified, but I think that from my understanding of it, IQ tests, which are supposedly to measure how smart you are, really don't measure smartness and creativity because you know as well as I, there are people that are incredibly smart in one field that are really stupid in another field. I've always wondered about people that spend their lives pretending to be other people. In other words, actors. Everybody considers that they're smart, and in a way, they are. They're very skilled in portraying other people. That's what they do. But why the heck do we listen to them on political matters when they have no idea what political matters really mean? We have people such as Bob Barker. He was the host of The Price is Right, testifying in front of Congress about I think it was something about saving the elephants or something like that. He was a big animal rights sort of guy. Why should his opinion matter when he is most famous for hosting game shows? Unless he has established his credentials some other way. If he has, yeah, let's listen to him. But just because he's smart in one area doesn't mean he's smart in another one. So smart is a very fuzzy linguistic variable. Continuing with the list, fast, slow, hot. You go, whoo, that's hot. Now, hot is ordinal. You can measure how hot something is by measuring the temperature, and same thing with cold. And the same thing with tall and short. You can always talk about the how tall somebody is in terms of meters or feet or whatever. So what do we do? We can see that we prescribe different measures to different things. We had the idea of, for example, the distance from LA to Chicago, and we just had a number of different cities, if you will, LA, Chicago, New York, and London. What about though if it's a continuous sort of idea, which such as short? Short, well, we could assume that whatever the membership is for short, that the shorter you are in terms of feet and inches, that the lower the membership will be in the set of people that are short. That's a fuzzy logic. So here's how we do it. We apply something called a membership function. And here's an example. By the way, this one is wrong. The first one, u sub b x 1 over x minus 2. And I'll tell you why it's wrong in a second. Um, this is a wrong membership function, but a membership function should go from 0 to 1. 0 means it's not in the set at all. 1 means that it's conclusively in the set. We don't have to worry about it. Anything in between, it's partially in the set, partially outside of the set. So we can talk about the numbers near to 2. And the reason this first one is wrong is because this one goes to infinity when x is equal to 2. And as we said, fuzzy membership functions can only go between 0 and 1. Again, 0 corresponds to no membership in the set. 1 corresponds to total membership in the set, and the other ones are various degrees. Um, there's another one here which is better. And just like with the fuzzy membership function for cities close to LA, your fuzzy membership for numbers close to 2 or near to 2 is going to be different than mine. And I'm going to come up with e to the minus x minus 2. Okay, that's a nice function shown here on the right. And that's a membership function that maxes out at 1 when x is equal to 2, because yes, x is equal to 2 is a number near to 2, so it's totally within the set, right? So you can see that right here at the peak, that's at 2. So 2 is very close to 2. In fact, it's right on the mark. And so therefore it has a membership of 1. And then the farther away you get from 2, the farther you get away, and you're not near anymore, if you will. So this is a fuzzy membership function. And again, its assignment can be arbitrary. You're going to choose a different fuzzy membership function than I am, but that's okay because fuzzy logic is able to deal with deal with these disparities, as we'll talk about. And by the way, this is the same way that humans think if you think about it. You might say that somebody is tall and somebody else says, no, he's not tall. So he's going to have a different membership function than you do. Your membership functions will still have the same monotonicity, if you will, right? And I think that anything that you choose in terms of a fuzzy membership for numbers near to 2 will probably always max out at 1 for an x is equal to 2 and then diminish as we go away from 2. So that's going to be a common trait to all of our fuzzy membership functions, if you will. Now, there's a number of interesting properties of sets. Um, and let me give you an example here. One of them is the idea of a subset. You're all familiar with a Venn diagram where you have a set, and then inside the set is a subset. So can we have fuzzy subsets? And according to Zade, yeah, we can. And here's how we do the fuzzy subsets. A fuzzy set A is said to be a subset of B if the membership function of A is always less than or equal to the membership of B. An example is, for example, B is far and A is very far. So very far is kind of a subset of the idea of far. And so if we are to, excuse me, stupid phone. So if we are a fuzzy subset, then the fuzzy subset must have a membership function of less than or equal to the set that it's at. For example, this is used quite a bit, is since the number of the fuzzy membership function is always between 0 and 1, if you square a number between 0 and 1, you always get a number which is smaller. So sometimes people say, well, what we're going to do is we're just going to square it, and that's going to be the membership function for the subset, since all of those numbers are going to be reduced. And notice what it does also. If u sub b is not in the set, then the subset, it's not also going to be in the subset because 0 will map to 0 and 1 will map to 1. If it's totally within one set, it's totally within the subset. So this is an example of the idea of a fuzzy subset. Now, we are interested in crisp membership functions that are either 0 or 1. For example, numbers greater than 10. That's a crisp number. And that number greater than 10 is a crisp set. So here we have a crisp set as opposed to a fuzzy set. A crisp set, you're either in the set or you're not in the set. So the membership function is always 0 or it's 1. You're either not in the set or you're in the set. So numbers greater than 10, anything greater than 10 has a membership function of 1. Anything less than 10 has a membership function of 0. So we can see that so-called crisp sets, or crisp logic, if you will, is a subset of fuzzy logic, because we can talk about conventional sets as fuzzy sets, and the membership functions are just binary. They're either 0 or 1. You're in the set or you're not in the set. Here's what I'm going to ask ChatGPT. I'm going to say, list a set of dangerous weapons ranging from a kitchen knife to a thermonuclear bomb. Okay, let's see what happens here. Okay, here we go. Kitchen knife, pocket knife, a blunt object, a baseball bat. How about that? A crowbar, pepper spray, taser or gun. This is pretty good, right? A shotgun, a semi-automatic rifle, bolt action high power rifle, machete. Now, I don't know where you guys are at, but all of these are dangerous, but they're all fuzzy linguistic sort of variables in the sense that you and I could go and ascribe to each one of these a degree of danger from a scale of 0 to 1. And the last one at the bottom is a fission nuclear bomb atomic. And then there's actually a thermonuclear bomb, which is otherwise. Now, there's people in our country that say we should take away all of the guns of people. And I understand that. When I was in Hong Kong and I mentioned that I own firearms, I'm a big Second Amendment guy. I own firearms. Their eyes got big and their jaws dropped. They say, "You own guns?" I said, "Yes." He said, "Nobody in Hong Kong owns guns, and we're safe. We're always safe because nobody in Hong Kong has a gun." Well, the problem in the United States is there's millions and millions of guns, and how you going to get those guns back? But that's a different thing. So the Second Amendment of the Constitution says something interesting. It says that we should not have we should not have our right to bear arms infringed. Yet they are. Okay, so let me ask you this: do you think that a taser or stun gun should be denied to a citizen of the United States? Um, I don't know. Different people have different opinions because everybody has a different fuzzy membership assignment of this on the set of dangerous weapons. It's usually a 0 to 1. A single shot pistol, a service or a compact gun, a shotgun. I got a shotgun, a semi-automatic rifle, and I have one of those. I just lent it to my son-in-law. Bolt action high power rifle, which is a sniper rifle. I would actually put after this. It didn't include it. I don't see it here as a machine gun, which is an automatic weapon. That's where you pull the trigger once. It goes boop 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 boop. You don't have to pull the trigger numerous times. It says a machete or an axe is even more dangerous than a bolt action power rifle. I don't know if I would agree to that, right? So here's my point that I want to make. We are going to set a threshold because laws cannot be based on fuzzy logic. They should be, but they can't be based on fuzzy logic. So therefore, making a law means that we have to choose a place where we don't where we outlaw things. Should a citizen be able to have a fission nuclear bomb? I don't think so. I don't think they should be able to have one. I did meet a guy on a ride share one time that said, "Well, heck yeah, we should be able to have thermonuclear arms if the government has them because we might have to someday fight the government." I don't agree with him. I don't think we should have thermonuclear arms as citizens. I don't think we should have biological weapons, chemical agents, landmines. I don't think that we should have landmines. I don't think we should own rocket propelled grenades. We're getting a little fuzzy here. I don't know. An improvised explosive device simply by the fact that they're terrible. Fragmentation grenade designed to kill or injure multiple people by shrapnel. By the way, did you know that shrapnel is named after a guy named Shrapnel? The guy that invented shrapnel is the namesake to the idea of shrapnel. Machete axe, a bolt action high, a semi-automatic rifle, a shotgun, service handgun. Okay, here's the point. Everybody is going to make what is called an alpha cut. An alpha cut is deciding where on this list are things too dangerous and where they're not. They want to take the fuzzy set and they want to make it into a crisp set, and laws are made on crisp sets. So I think we can all agree that roughly that this lists the least dangerous to the most dangerous, right? And I think everybody agrees we should be able to have kitchen knives. I think that everybody agrees that we should not have thermonuclear weapons privately, but everybody disagrees to where on this list we should draw the line. This again is referred to as an alpha cut because an alpha cut takes a specific fuzzy membership function and it says anything that's bigger than that we're going to call a one, anything less than that we're going to call a zero. So when we're talking about implementation of the Second Amendment, we're talking about where the alpha cut is. We all basically agree that there's some weapons that are more dangerous than other ones, but the question is where do we draw the line? Where in this set of fuzzy linguistic measurements of danger do we draw the line? So this is very, I don't know, I find this is very interesting. Another example is drunk driving. You're you're drunk driving. I have no idea what the blood alcohol count is for the definition of drunk driving, but I can tell you it's probably different in the state of Texas than it is in the state of Massachusetts. I suspect that the percentage of alcohol is different in different states for the legal definition of drunk. And you might disagree on that, but this is just an alpha cut. We all agree that the more blood alcohol you have, the more drunk you are. It's just the case of where you're going to draw the alpha cut. Where are you going to make this fuzzy set into a crisp set? Where are you going to do the threshold? And by doing the threshold, we make it into, if you will, a crisp set. So this crisp set is determined by a fuzzy set, and then you set a threshold, everything above the threshold or below, in this case, above the threshold for blood alcohol count. Everything above it is drunk. Everything below it is not drunk. And in a way, this is kind of a stupid law if you think about it. So if you have a blood alcohol count, I don't even know what percentages there are. But if it's just a teeny bit less, you're not drunk. No, it doesn't make sense. If you're just a teeny bit, if you're just on the edge, but a little bit below, you're not drunk. It seems to me that is what the law is, and laws like to make decisions based on alpha cuts, if you will, on conventional crisp sets. Now, one of the things about fuzzy membership is there's many times it's confused with probability. I mean, with probability, you have probability density functions, you have cumulative probability density functions wherein a person has a certain probability of doing something, and fuzzy membership functions are also on the level from 0 to 1. But fuzzy is a very different measure than probability. What I want to do is to try to differentiate in your minds, if you have this confusion, about the difference between fuzzy logic and probability theory. So fuzzy is not equal to probability. Here's an example. Billy has 10 toes. The probability Billy has 9 toes is 0. The fuzzy membership of Billy and the set of people with 9 toes, however, is non-zero. Okay, so that's one example. Here is another example, which I got from a pioneer in fuzzy logic, a guy named Jim Besnick. He said, you come upon in the desert a couple of bottles and you're just dying of thirst. So the fuzzy membership of the percentage of rat poison in one bottle is 1/2. That's the fuzzy membership function. In the other one, it has a probability of 1/2 of being rat poison and 1/2 of being pure water. So it's a 50-50 chance. So on one hand, you have what you know is a mixture of rat poison and water, and that membership function of the degree of rat poison in it is 0.5. And the other one, which is probabilistic, the first one is fuzzy. The second one, which is probabilistic, says that there's 50-50 chance of it being rat poison, 50% chance of it being pure, clean, potable water. The question is, which one would you drink? They both have a value of one half. One half in one case is the membership function. In the other case, it's the probability. I don't know about you, but I would not trust drinking out of a bottle that has a fuzzy membership function of one half of liquids containing lots of rat poison because I know it would have rat poison in it. I don't know how much, but it would have rat poison in it. I would probably do the coin flip and I would choose the bottle which was one half, had a probability of one half of being rat poison, one half of being pure potable water. And I would go for the one half. I would take a drink and go for the 50-50 flip because I have 50-50 chance of getting pure drinking water. None of the other cases am I going to get pure drinking water. None of the other cases am I going to get something which lets me survive. In all of the other cases, I'm going to get rat poison. In the fuzzy membership, I'm going to get it in a diluted form. In the probability case, I'm going to get it in pure form. So that's another example of the difference between fuzzy logic and probability. You will notice again that probability goes between 0 and 1. Fuzzy membership function goes from 0 to 1. Probability talks about things which are happening in the future, except for Bayesian logic, things which are happening in the future. Fuzzy logic, on the other hand, looks at things the way they are and measures the fuzzy linguistic variable, which is describing whatever is going on. So that's another example. Now, it turns out that you can mix probability with fuzziness. And if you weren't confused before, now you will be, because it turns out probability can either be crisp or it can be fuzzy. Really? Yeah, the probability that a fair die, if you roll a fair die, the chance you will get 6 pips. Pips are the little dots on the die. The probability that a fair die will show 6 is 1 out of 6, right? There's no argument at all. Everybody's going to say, yeah, the chance of getting a fair die showing 6 pips is 1 out of 6. This is a crisp probability. All credible mathematicians will agree on this exact number. But if you go to a weatherman on one streaming channel and they say the forecast of the probability of rain tomorrow is 70%, that's a fuzzy probability. Why is that? Because they're just estimating. If you go to another channel, they might say, well, there's probably a 60% chance of it raining tomorrow, a 60% probability. And if you go to another channel, they might say, no, it's going to be 72%. So everybody's going to have a different interpretation from the data that they're observing that it's going to rain tomorrow. All the mathematicians in the world will not agree to this result. And therefore, the probability that you get from the different weatherman is fuzzy. So probability can be fuzzy. I thought that was interesting. This was pointed out to me by a guy named Piero Bonassani, who was a fuzzy expert who was worked for General Electric. He was a fellow. He could kind of pop around General Electric and do whatever the heck he wanted to. And he was in charge, by the way, of taking all the General Electric washers and dryers and transforming them into a fuzzy logic base, according to the Japanese. Interestingly, historically, fuzzy logic was not adapted in America. Rather, it was the Japanese that originally got a hold of the idea. And there were some Japanese, there was a Japanese surge in the application of fuzzy logic. So they began to apply it to everything. And I went over to Japan one time, met a good friend of mine, Toshio Fukuda. He was a professor at Nagoya University, one of the imperial universities there. And he said, oh, yeah. He says, Zada was actually very famous in Japan for doing that. I said, really? So I was invited over to Toshio's house, and I met his daughter. And his daughter wanted to come up and practice English on me. So we were practicing English together. And so I asked her if she had ever heard of Latvizada or had she ever heard of fuzzy logic. And she went, no. I said, you've never heard of fuzzy logic? And Tochio interjected and he says, have you heard of fudgy logic? So I was pronouncing it wrong. The Japanese interpretation was fudgy. So he said, "Do you understand fudgy logic?" She went, "Oh, fudgy logic. Yes, yes. It's all over the place." And if you looked at the commercials at this time in the 80s and early 90s in Japan, you would actually see fuzzy this, fuzzy that all over the place. Zada was kind of celebrated in Japan. And it was only after the development in Japan of fuzzy logic that it became popular in the United States. So that's basically what I wanted to talk about today. I wanted to advertise what we're going to talk about next time. As you know, when we have fuzzy sets, we have criteria for things such as ands and ors and complements. We know what anding two sets are, two crisp sets. If we and two crisp sets, we look at the intersection of the two crisp sets. If we or them, we look at the union. If we take the complement, we look at everything outside of the set and say that that's the complement. Can we extend this? Can we extend this to fuzzy logic? Yes, we can. And we're going to extend the idea of ands and ors and complements. And there's some criteria that we must follow. Number one, it must meet the crisp boundary conditions. We have seen that crisp sets are a special case of fuzzy sets. So if we come up with a method of doing, for example, the logical operation of and for fuzzy sets, it better reduce to the definition of ands for crisp sets, the sets that we're all familiar with. It must be commutative. If you do A and B, that's the same as B and A. If you do A or B, that's the same as doing B or A. So it must be commutative. It must be associative. And if you're familiar with Boolean logic, that the and is distributive over the or, and the or is distributive over the and. And so we have to make sure that that application also applies. And it's the idea. It should be idempotent. I love this word. Idempotent means if you do it twice, it's the same thing as doing it once. And we'll talk about more of the definition of that. And it should be monotonic. We'll get to the idea of monotonic later. But these are the things we're going to delve into next. We have these ideas of this operation of ands, ors, and complements. So if we say, this guy that we talked to was very tall and he sure could run fast. You'll notice that we have two fuzzy linguistic variables. He was very tall and he could run very fast. Two fuzzy linguistic variables. So how do we take the fuzzy membership function of tall people and do an and with the fuzzy interpretation of fast people? So that's what we're going to do. That's what we're going to do next time and talk about the mathematics behind that and messing around with fuzzy membership functions. Okay, I think that that's probably this is probably a good stopping place. Anybody have any questions at all?
So the difference between fuzzy logic and probability, at least my interpretation, seems to be a crisp logic set or a probability is this is this is the number we can mathematically prove this, whereas a fuzzy logic system is more so an estimation, usually by a human entity. Is that an understanding? Is it a working understanding?
I think that it's better to think of them not as kind of complementing each other, but I think they're both definitively, distinctly different measures. They're measuring totally different things. Fuzzy logic is looking at basically the fuzzy linguistic variables that we're talking about. At least that's its application to to the engineering that we're talking about. And this is the stuff which exists now. So I can say that this person is tall and this person is fast. I can say that and it's now. That's different than asking what is the probability that this person is tall and what's the probability that this person is fast. Those are two distinct measures of the same phenomena, but using a different metric, if you will. One uses the probability and the probability out of ignorance. The other one uses fuzzy membership function out of expertise. We have expertise in what we're talking about. We all know what we mean by a tall person or a fast person. However, if we talk about the probability somebody is tall, we don't know what that person is, whether they're tall or not. We're operating out of a state of ignorance. I think that that's one definitive issue. They're two distinctly different concepts. And I think that the more you try to marry them, the more confused you will get. That's the reason that I talked about fuzzy probabilities in order to confuse you more. There are probabilities that are fuzzy, but they are two distinct ideas being applied to the same thing. I don't know if that answers your question. I think that was Riley, right?
Yes, sir.
Okay. Did that
All
answer
right.
your question at all?
Yes, sir, it did. Two distinct things, not necessarily intermingled. Not yet, at least.
Yes. Well, they are intermingled, but I think it's best if you think of them as two separate things, because if you could start confusing fuzzy membership functions with probability, it's going to screw you up.
Okay, will
Okay.
do. Thank you so much, sir.
Any other questions? Okay. Hearing none. Thank you for your attention. Be of good cheer, and we'll see you on Thursday. Bye bye.